Yes, so hi everyone. So I'm indeed going to be talking about approximate inference for neuroprobabilistic logic programming. So let me first clarify that second part of the sentence. So what exactly is neuroprobabilistic logic programming? So the idea is that symbolic and subsymbolic AI have very complementary strengths, right? So at the one side you have your pattern recognition power from deep learning, like it works quite well on highly dimensional like subsymbolic data. On the other hand, we have the reasoning power of logic. So, of course, we've also seen that more and more that deep learning and reasoning is not very successful. On the other hand, of course, logic doesn't really work well on highly dimensional data. So the idea that we have is that we integrate neural networks into probabilistic logic programming. And so a few years back now, we introduced DPLA for this, which is the probabilistic logic programming language PROBLOG extended with the idea of the neural predicate. So let me kind of show what it means. So imagine we have a very simple vision task to be solved by deep learning and a simple reasoning task together. So we take the two MNIST images, for example, and instead of trying to label each individual digit, we have to label the sum of both. So then it involves a classification of the images and a very simple step of logic. So the first line you see below there, so indicated in yellow, is the how we would then introduce this neural predicate in our logic program, basically saying that the first part, so the probability of this atom comes from a neural network that takes as input a certain image. The second line would then be a simple prologue line that defines the addition basically on those two classifications. And then we would be querying for certain of these addition examples. However, so there are some issues with this neural probabilistic logic programming, because we have to reason probabilistically over neural network outputs, and we have to consider all of the possible outputs. So that can quickly become quite expensive, since we have to consider all of the proofs of each query, because we're doing exact inference. And this number of proofs can grow very fast. However, although there are a lot of proofs, in a lot of the tasks that we consider here, only one proof is considered interesting or correct, namely the one where you assign all of the correct classifications to the digits. So if we take the same example and we basically use longer and longer numbers where they are then represented by lists of images that each have to be classified separately, we see that if the length of this number grows, the time spent on grounding or proving explodes quite rapidly. So that's, of course, limits the applicability of such a system. So that's why we introduced DPLA star in this work. And the idea is, I mean, it's not a new idea in a sense, because star AI approaches such as PROBLOG also suffer from this scalability issue. So we based it on some of the work of that, where we use only a subset of all proofs. Now, what we also do differently is that we replace the normal search for proofs by an efficient search for the best proofs using a star search. So it means we can also include a heuristic. And the idea of that is very simple. So if we look at the probability of a partial proof, so that means that, so we're looking at something that's either a query, a proof that's partially completed or even fully completed, and look at the probability of that, we see that, okay, we can separate it into the facts that we've already used in the proving and the goals that still need to be proving. And by taking like the log of this, we can see that quite clearly. We get something that's quite similar to the formulation of the F value in a star search. So we're using that. And then all that really needs to be done is defining some heuristics for the efficient search. So that's really trying to approximate the probability of the goals given the facts that we've already used in the proof. So of course, I mean, some basic results tell you that. So if the heuristic is admissible, you will always find the best solution, but also we're going to approximate that. So we're not very generally interested in admissible heuristics because they're, well, not usually quite powerful. But then even then we know that the error on our solution is bounded. So in this work, we've considered 3 heuristics. So uniform cost search, which is admissible. Then the geometric mean heuristic, which uses a special assumption, namely that all of the probabilities used in a proof are similar. And in the paper, we actually motivate why that makes sense in the specific setting of neural symbolic that we often consider. Then also, we want to leverage the fact that we are also using neural networks to introduce a parametric heuristic, where we actually are going to use neural networks to estimate the probability of some of the goals using neural networks, which allows us to leverage the similarities between separate goals that we've already seen during proving. But of course, this setting is mainly interested in the learning. And using approximate inference together with learning requires some special considerations, because if you're selecting a lot of wrong proofs at the start of learning mainly, that can really be an issue for convergence, because if you're selecting the wrong proofs because you're working with a subset and the correct proof is not among them, then you can actually enforce wrong classifications, and it's quite easy for the model as an entire in its entirety to converge on a local optimum. So we are considering in this work some solutions based on curriculum learning and exploration. So for this, we introduce an additional exploration term based on the UCB algorithm, where we extend the probability of our facts, basically of our neural predicate facts, to include an additional term based on this exploration, which kind of accounts for the underestimation that the neural networks can have. So basically, the idea is to make the search, or the heuristic at least, more admissible, so that it actually tries to find more proofs in the hope that the correct proof is among them more often. And then we can also use the information from the proving process to train the parametric heuristic. So while we're training and learning our normal neural networks, the neural networks behind the heuristic can also be further optimized. So if we look at the experimental evaluation, we use 3 experiments. So the Amnesty edition experiment that we borrowed from the DPLA paper and also used here as an example. So for longer and longer lists. Then we also considered a more complex one, which we call the multi-instant Amnesty edition, is where that instead of knowing that, okay, for this pair of numbers, the sum is 7, we're now saying like we have a bag of pairs of numbers, and we know that at least for one of them, this is the correct result. So here it's also about finding the correct element in this bag. And then we're also to have a comparison with other neural symbolic frameworks using handwritten formulas, which are quite similar to the Amnesty edition, but slightly more complex, because we now have several operations and we also have to find the operation itself. And finally, to showcase it on a larger task, we're using the computational language understanding with text-based relational reasoning, or the clutter data set, which is of the form where you get a set of sentences containing family relations, like Charlie has a brother called Bob, and Bob went to visit his mother Alice. Then you could ask, okay, what's the relation between Alice and Charlie? So you would have to use some background knowledge to reason about this. So here we consider that knowledge defined, however, which is not very special, because we know how family relations work. So as a result, so first, this was all about making inference more scalable and tractable. So if you look at the inference speed for the first experiment, the Amnesty edition, so on the x-axis, we have the number of lengths. So previously we saw it really explode. So if we look at these lines, so we have the red and the orange and the green, that's the original DPLA and also our new algorithm, but with the uniform cost search. And the 0 here in brackets means how many examples we use to pre-train it, so curriculum learning. We see that it really performs quite poorly. We also compare that to a different framework, Neural ASP, which does something quite similar to DPLA, but with a more scalable basis. We see that these, as expected, blow up quite quickly as the number length increases. So if we look at DPLA star, here in brown, we have the geometric mean heuristic that we've considered. So even without any curriculum learning, we can see that it actually performs a lot better than the proplog originally. So, and also performs better than neural ASP. So that's good there. And then we can see if we actually use a tiny bit of examples, so 16 labeled examples of MNIST stages to pre-train the neural networks, we can see that that's actually enough to really make this search a lot more efficient, so we can actually handle numbers up to length 4 and 5. So we see that the curriculum learning is very important, even if we have very little examples. Also, here we see that basically the time required to answer a query drops quite significantly as the accuracy of the neural network rises, because the search itself is guided better. With respect on to accuracy on that same task, we see that, okay, of course, the proplog from a task it can handle performs really well. So exact inference is basically the best you can do. And if we don't use any exploration, then we said DPLA star has some trouble converging, but in the end also converges quite reliably. If we're using some pre-training, we see that actually it also performs equally well as normal dproplog. Okay, sorry, I forgot the slide here. But we can also see that if we look at the orange and the green line, that if we have some exploration in there, it's a bit slower to pick up because of the exploration, but in the end, it actually achieves a higher accuracy than without exploration and also more reliably. Now, considering the parametric heuristic, this is on the multi-instance setting. We can actually see that, okay, so we have two cases that we show here. So with no pre-training whatsoever, and some in blue, and the top one in brown is with pre-training and some exploration. We can see that actually this is a very hard task. And so normally it's infeasible to solve, but with a pre-trained parametric heuristic, it's actually able to guide the proving process towards the correct proof, and we're actually able to learn something. And in the second figure B, we show the accuracy of the heuristic itself. We can also see that during training, it's actually also able to further fine-tune itself. It still achieves quite a low accuracy, but the fact that it only uses this as a heuristic and it's still doing a search around that, it actually allows it to still perform quite well. So for additional details, I'll be at the poster session later today. So are there any more questions for now?